Oh, is it on? We're going to do artificial gravity, and then we're going to do banked curves. So I'm going to switch the order because I want to make sure that we have enough time for the artificial gravity in case you guys find it difficult. Okay, so here we go, artificial gravity. Okay. If we want to send a spaceship to outer space, that is a spaceship that's not near enough any planets or stars that people are getting any significant gravitational pull, then we're gonna, and we want them to be on these spaceships for a long time, like in that movie WALL-E, you know, that we're gonna have to figure out a way for there to be gravity, and it's gonna be artificial gravity because there's not gonna be any actual planets causing the gravity. Well, unlike Star Trek or Star Wars land, where you can just have a spaceship looking like this and everybody on board somehow magically has gravity, you tell me, how are we going to obtain artificial gravity in real life? What am I going to have to do to these spacecraft? Yes, Leilani is making a motion. How many people say rotating? Yeah, that's it. Has anyone ever seen the movie 2001: A Space Odyssey? Okay, yeah, that's how they achieved it. You had a rotating spacecraft. So that's it. Artificial gravity means rotating spacecraft. That's the only way it's going to happen. Okay? Here's my spacecraft. Here's the center of the spacecraft. Here's me. Okay? That spacecraft is rotating. I'm in outer space. I am not near any planets or stars. Tell me, what forces are acting on this guy? Raise the hand so I don't raise it. Call him. What force is acting on this guy? Yes?
Centripetal force.
Okay, but what's providing the centripetal force? Because there's no actual force, you know, that's specifically centripetal force. It's just one of our known forces that provides the centripetal force. So what's making this guy go round and round in a circle instead of hurtling out in a straight line, tangent to the circle? Thank you very much, Charlton. Normal force, just like garments in a dryer, correct? So I got normal force acting on him. Good. Are there any other forces acting on this guy? How many people say no? Good for you. There aren't. Now, I'd like to take a step away from this for a moment, okay? This spaceship is rotating, and there's a lot of people who think, okay, then there's friction. There must be friction on him to keep him rotating. But I want to let you know that only happens when the spaceship is starting out. That is, when the spaceship is at rest, and then you have to get it rotating, then this dude, because he's accelerating, there's going to have to be friction between his feet and the spacecraft. But once the spacecraft is already rotating, and it's not going any faster or slower, then there's no more friction. For the same reason that, you know, on Earth, you know Earth rotates, right? Does anyone know approximately how many miles an hour each one of us is going because of Earth's rotation?
30,000.
Well, no, not 30,000 miles an hour. That's
meters per second.
That was how fast the Earth is orbiting the sun. But I'm just talking about due to the Earth's own rotation about its own axis. Do you know how fast we're going? I'll tell you, if we were on the equator, it'd be 1,000 miles an hour, right? So we those of us in the northern hemisphere, we're not going 1,000 miles an hour, we're going somewhat less, but we're still going pretty darn fast. But do I need friction to make me go 1,000 miles an hour? No, because I'm already going 1,000 miles an hour. You see what I mean? So there's no friction force on me right now. I can't claim that because I'm rotating 1,000 miles an hour, friction is making me rotate 1,000 miles an hour, because there's no friction force on me, because I don't need friction. Again, it may sound stupid, but because I'm already going 1,000 miles an hour. I don't need friction to make me do it. I'm already doing it. You see what I mean? I'm already in that motion. So I'm just telling you that. Now I'm going to come back to the rotating space station. I'm just telling you this to convince you that there's no friction force on this guy, not while the station has already been spinning for a while. Only during the time when the spaceship is acquiring its spin do we have to have friction on the guy. Okay, so that's all we got is normal force. Okay, and tell me, what if he was standing on a trap door and the trap door opened suddenly? He wouldn't be going around in a circle anymore. What would he be doing?
Go out.
Yeah, he'd go off at a tangent, on a tangent line. He'd be flung out this way. Okay, great, just in the same way that when I did my yo-yo and I let go, it got flung. You know, if I let go at the bottom of the swing, the yo-yo got swung out that way. Okay, great. So let's go ahead and do an example. Example number 1. You want an apparent weight equal to half your true weight you want an apparent weight, half your true weight. The spacecraft has a radius equal to 300 meters. Find the RPM of the spacecraft that does this. Find the RPM of the spacecraft that does this. Well, this is a pretty complicated problem. Is there some procedure that you would recommend I follow? Thank you. Free body diagram? Yeah, and then what? Thank you. Sum of the forces equals MA, right? No problem, cannot be solved with that process. So here we go. I got my free body diagram. That's all there is. By the way, this normal force, are you okay? What's that equal to?
1/3.
What's normal force? And whether you're on an elevator or whatever, what's your normal force? What's another name for your normal force? Yeah, your apparent weight. When they say you want an apparent weight of blah, 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 what they're really saying is you want a normal force of blah, blah, blah. So this normal force is your apparent weight. Okay, so let's go for it. Sum of the forces equals MA. The only force acting on you is your normal force. That's it. That's all there is. Okay. When I'm going around in a circle, you know the A is V squared over R. Great. And now my normal force, I want it to be half my true weight. So do you mind if I substitute 1/2 mg, that is half my true weight, in for the normal force, because that's what I want my apparent weight to be, equals mv squared over 300 meters. And I can solve for v. By the way, you notice the m's cancel, so it doesn't matter if it's you or me who's on that spacecraft, we'll both feel 1/2 of our true weight. Okay. So I got 4.9 times 300, take the square root of that, 38.3 meters per second. So that's how fast I need to be going so that my apparent weight is equal to 1/2 my true weight. By the way, this is about 80 miles an hour, right? When I give you a speed in meters per second, if you double it and add a little bit, that's going to get you your speed in miles an hour. Is it going to feel like I'm going 80 miles an hour? Am I going to think, wow, I'm going so fast? No, because we're going 1,000 right now and it doesn't feel like anything, right? So he'll be okay going 80 miles an hour. But let's find how many RPM that is, because I want the RPM. Okay, so I've got 38.3 meters per second. Okay, and I'm going to multiply by 1 revolution in 2 times pi times 300 meters. Right, that's the distance you go in 1 revolution. And then I want it in RPM, so I'm going to multiply by 60 seconds in 1 minute. You guys okay with that? And so I get divided by 2 divided by pi divided by 300 times 60. I get 1.22 RPM. So tell me, is this spaceship rotating very fast? No, 1 RPM? That's like the Seattle Space Needle, right? Has anyone ever been on the Seattle Space Needle? where you're in that rotating room, you know? Well, yeah, that's the Seattle Space Needle. That's not very fast at all, you know? And yet, you're rotating fast enough, because the spaceship is big enough to give you a significant apparent weight. Hey, you guys ready to do a problem like this on your own?
Yeah.
Okay.
All right, here we go. Example number 2, I'll walk around and help you. Example number 2, you are in a 1,000 meter radius spacecraft. That rotates at 0.75 RPM. What percent of your true weight is your apparent weight? Okay, good luck. And hopefully everyone realizes you're gonna have to convert RPM. You're gonna have to convert RPM into meters per second. Then you're gonna plug into this formula, and let's see what you get. Who is it? We should just rip it up and give him a 0.
Aw. I like having an A in physics.
A 1 kilometer radius spacecraft. So it's like a Death Star. Let's see if you got the speed. Yeah, you got the speed right. Now you're ready to plug into F equals ma. Coolio. Good. Yeah, go for it. Make that conversion. Plug into V squared over R. I felt your presence behind you. Glad I didn't step on you or something. Ooh, multicolored. Hey, yay. Everyone's doing their conversions. Everyone's doing their conjugating their verbs. You want to do that?
Good job, Brianna.
These are regular forms. What is that? Oh, imperfect predator. Oh my God. What did you do? What's inside Spanish? Was that? Oh, okay. Yeah. I only went up 3 years of Spanish. I never learned imperfect predator. Yeah. I'll never learn it either. Never in my life. I spent 2 years in Honduras and didn't even learn how to speak Spanish. It's pretty damn 37. We'll have to do the bank curves later. Spend too much time talking about the. Oh, you're so smart. Don't ever change.
Is that the right answer?
Yeah, yeah, 62%, about 63%. Yeah. Good, just plug it on in, Z squared over R. And you'll get a value for G, which is a percentage of the true G. So long, 2 pi R. Okay, yes, that's what happened. So, wait, where's your,
Still
how's your
at
RPM converted to velocity? Where'd that happen? Or that's happening here? And you got, okay, that's revolutions per minute. So that's correct, but you know, it should be, since it's revolutions per minute, you need 1 minute 36 seconds. you know, your radius is 1,000, the V is 78.5.
Oh, but
So let's pass it.
yeah.
2 minutes.
The percentage of the.
I really didn't need that. Oh, you guys will be fine.
What? I got one.
Okay.
Yeah, there's like, yeah, no, just the decimal. Yeah, I but not much. When you're walking, I thought this was this. Thanks,
Okay, hey guys, the bell's gonna ring soon, so I'm hoping you're okay with this conversion from RPM to meters per second, 78.5. Then you plug into here, and I ended up with my normal force being my mass times 6.2 meters per second squared. So tell me, how do I answer the question, what percent of my true weight is my apparent weight? What should I do?
You like cancel out the masses.
Oh, okay, so you want me to call this M times G where, I don't know, you want me to call this mg?
Yeah.
Okay, that would be my true weight. That they're not really equal to each other.
Okay,
But then what? Okay, so I cancel out the masses, then what?
okay, so me and Azina, like, we feel like cancel out the masses and say, like, you're just left with 9.8 on that side, and so, like, you put X, like, just to,
So did you end up just dividing that number by 9.8?
yeah.
Okay, so did anyone just think, hey, let's go ahead and get my apparent weight over my true weight like that? Just make that ratio. My apparent weight is 6.2 m, my true weight is 9.8 m, and now the m's cancel? Anyone kind of think of it that way? Well, however you do it, divide 6.2 by 9.8 and that gets you your percent. You're getting 63% of your apparent weight. And if you want to do it Amani's way, that's fine. Just be aware, you know, that this whatever percentage of 9.8 this is, that's a percent of the true weight you're going to feel is your apparent weight. All right, we'll talk about banked curves tomorrow, I guess, or Monday or Tuesday, I guess. And that's it. Good luck on tonight's homework. Thank you. Bye.